Alright, this is exam 1 from spring of 2009. In this first question it says which of these vectors A through E represents the net force on this 2 nanocoulomb charge due to the -3 and the +6. Well, just want to sort of represent the vector. So here you have a +6 and a +2, and so the force acting on the +2 nanocoulomb charge is going to be in this direction. Alright, and there you have a -3 nanocoulomb charge and a +2, and these two charges are going to attract to one another, and the force on this charge is going to be in this direction. Now this force due to the -3 is half the magnitude of that due to the +6, because -3 is half of 6, or rather 3 is half of 6. So the force vector is half the length of this force vector. So our net force then could either be A or B, but because this vector is bigger, it has to be B. So the answer here is B. Proton is accelerated in an electric field of 1,000 newtons per coulomb. If the proton is initially at rest, what is the proton's displacement after 1 × 10⁻³ seconds? Well, the force is equal to the charge times the electric field. That's the magnitude of the force. It's equal to the charge times the electric field. This is 1.6 × 10⁻19 coulombs. That's the charge of a proton, and then this is 1,000 newtons per coulomb, which is the electric field, and that gives us 1.6 × 10⁻16 newtons. And we know from Newton's second law that this is equal to the mass times the acceleration. So our acceleration is just this force, 1.6 × 10⁻16 newtons, divided by the mass of a proton, which is 1.67 × 10⁻27 kilograms, and that gives us an acceleration of 9.6 × 10⁻10 meters per second squared. Now we want to know what is the displacement after 10⁻³ seconds. Well, displacement is equal to v0t plus 1/2 at squared, but it says it's initially at rest, so v0 is 0, so this is just 1/2 of a, given here, times t squared, which is 1 × 10⁻3, and that gives us our displacement of 4.8 × 10⁴ meters. And so that is option A, 48,000 meters. Okay, this figure shows 3 charges. The charge Q2 has -10 nanocoulombs. What is the charge of Q3? Well, if you want to count the number of field lines, there are 16 field lines going into Q2, and there are 8 field lines coming out of Q3. So we know that the magnitude of the charge of Q3 has to be half that of Q2, because there are half as many field lines coming out. So Q3 has a charge of either plus or -5 nanocoulombs. Well, plus is the only one given, so that must be it. We know it's positive because field lines emanate outward from a positive charge. And because Q3 has field lines coming out of it, that means that Q3 is positive, so it's +5. That's option E. This figure shows how particles respond to one another, and separately how A and C respond to one another. Which of these statements is true? Well, let's just go through them. A and B are like charges. A and B are attracted to one another, so they are not like charges. They are opposite charges. A and C are opposite charges. Here, A and C are repelled from one another. That means that they're like charges, so that's not an answer. B and C are opposite charges. Okay, if A and B are like charges, that means they're the same, and A and C are opposite charges, that means that they're different, then that means that B and C have to be different, because A can't be the same as B and then also be the same as C. So the answer here is C. And D is B and C are like charges, which is the opposite of C. So the answer is C. In this figure, a ball made of a conducting material is attracted to a positively charged rod. Very important that it's conductive, conducting, and positive. What is the charge of the ball? You can have 2 scenarios here. You can have a negatively charged ball, and it would be attracted to that, or you can have a neutrally charged ball. Let me show you what would happen with a neutrally charged ball. Here's the positive rod. Here's the neutrally charged conducting ball. You would get a charge set up on this where you'd have all the negative charges over here, and all the positive charges over here. So the net charge of the ball is neutral because it has equal number of positive and negative charges, but it's still attracted to the positive rod. So the answer is either negative or neutral, and that's option C. This figure shows two charged particles separated by a distance of 2 centimeters. What is the force on Q2? Okay, well, Q2 due to Q1 has a force in this direction. And we want to calculate the magnitude of that force. I know that it's in that direction because they're like charges, and like charges repel. Alright, so F from Coulomb's law, the magnitude of F is K Q1 Q2 over R squared. That's 9 times 10 to the 9th, which is Coulomb's constant. Q1, which is 50 times 10 to the minus 6 coulombs, and Q2, which is 1 times 10 to the minus 6 coulombs, divided by R squared, which is 0.02 meters squared, and that gives us our answer, which is 1100 newtons. Alright, I give you both 1100 and negative 1100. The answer here is positive 1100 because it's to the right. If I asked you, by the way, for the force on Q1, which is not what I'm asking, but if I did, this would be negative 1100. And this force is positive 1100. So the answer here is B. A proton and electron are in a constant electric field as shown. You release an electron and a proton at a point equidistant between the plates. Which particle has more kinetic energy when they strike the plates? Well, the potential is equal to the change in potential energy over Q. Alright, so since both of them have the same Q, and they're both experiencing the same change in potential, then they're both going to experience the same change in energy. Alright, so the answer then for this one is B, that they have the same kinetic energy. An ion is accelerated through a potential difference of 100 volts, has a potential energy increase by 1.6 times 10 to the minus 17 joules. Calculate the charge on the ion. Well, V is delta PE over Q, just like I had before. So Q then, which is what I want to know, is equal to delta PE over V. That's 1.6 times 10 to the minus 17 joules over V, which is 100 volts. And that gives me 1.6 times 10 to the minus 19 coulombs, which is a proton. And is answer C. What is the potential at point P in this figure? To find the potential, you just sum up the potentials from each individual charge. I want to know the potential at this point. And V is equal then to the sum of KQ over R, which is KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3. And I'll call this particle 1, particle 2, and particle 3. I'm going to factor out the K and put in some numbers. That's 9 times 10 to the 9th times Q1, which is 3 times 10 to the minus 6, over R1, which is 4 centimeters or 0.04 meters. That's this distance from that particle to that point, plus Q2, which is 1 times 10 to the minus 6. It's in coulombs, over 0.05 meters. That's this distance, plus negative 2 times 10 to the minus 6 over 0.03 meters. And put in the numbers, and you get 2.6 times 10 to the 5th. That's in volts, which is option C, 260,000 volts. Now, a big common mistake is that you leave out this negative sign, but when you're figuring out the potential of a collection of charges, the sign of the charges is important. You need to include that. Alright, which of these statements is true at point P, which is at the center of the square? That is the potential and the electric field zero or non-zero? Well, the potential is easy because it's not a vector quantity, so all we need to know is, are there equal numbers of positive and negative charges? And if so, the potential is 0. So there are equal numbers of positive and negative charges. There are 2 positive and 2 negative. So we know then that V is equal to 0, because the potential due to the positive charge is canceled out by the potential due to the negative charge. Now the electric field is a little more complicated. To find the direction of the electric field, you want to imagine a positive test particle at the point. So I'm going to imagine that I have this positive test particle at point P. And then for each of the Q values, I want to ask myself, what is the direction of the force that that positive test particle will feel? And that direction of the force is the direction of the electric field. So, for example, let's start, we'll call this 1, 2, 3, and 4, and I'll start with 1. If I have a positive test particle, it is going to be attracted to that particle. So my electric field is in that direction due to particle 1. Particle 2, that is this particle, has a force on a positive test charge that is in that direction, because they would be opposite charges and they would repel. Particle 3 has an electric field in that direction, and particle 4 has an electric field in that direction. So we have 4 charges that have the same magnitude of charge. They're either plus or minus Q. And the vectors all oppose one another, so the electric field is equal to 0. So that gives us the answer here, that the electric field and the potential are both 0. That's option A. Which of the following diagrams is potential on the x-axis equal to 0? Alright, well the first thing that you want to do is you look and see if you have equal numbers of positive and negative particles. So here you have all negative particles, so there is no way for the potential to be equal to 0. Now these other two, you have both positive, you have equal numbers of positive and negative particles. Alright, so for example here you have a plus 2 and a minus 2, plus 1 and a minus 1. However, let's say that we pick a point at this line right here. The potential due to this particle does not cancel out with the potential due to that particle, because the distance here is a lot shorter than the distance here. So those potentials don't cancel out, because remember, V is KQ over R, and if your R values are different, then you're going to have different potentials. So it's not that one. And for a similar reasoning, say pick a point here, you have 2 points, the distances to those 2 like charges are dissimilar, so the potentials do not cancel out. Now let me give you an example of one where it would cancel out. Let's say that you had plus 2, minus 2, plus 1, minus 1. Along the x-axis, the potential is equal to 0, because say for example I pick this point, the distance from there to there is equal, and so the potentials are equal and opposite, and so they cancel out. Likewise, the distance from there to there and there to there to the plus and minus 1 charges are equal. Those distances are equal, and so the potentials cancel out. Okay, the following graph is for potential versus position. If an electron is released at point A, what direction will it move? Well, I gave a couple of rules in class, and that is that electrons move from low to high potential. And protons move from high to low potential. Alright, so applying those rules, if we have an electron at this point, it wants to move from low to high, and as we discussed in class, if it moves in this direction, it's going to overshoot, and then it's going to come over here and want to move from low to high potential, and so it's going to just actually oscillate back and forth. So the answer here is A. The way that I always remember these two rules, let's say that you have these 2 charge plates we talked about in the beginning of this section. One side is positive, one side is negative. This is your high potential side, this is your low potential side. Alright, an electron is going to move in this direction, away from the low potential side. A proton is going to move in this direction, away from the high potential side, from high to low. Alright, and you can think about this just because the negative charge is repelled by the negative charges, the positive charge is repelled by the positive charges. So if that helps you, then so be it. Otherwise, just memorize these rules. Alright, what is the potential across the circled 8 microfarad capacitor? We know that capacitors in parallel have the same potential. So all these capacitors which are in parallel have a potential of 36 volts. So these two 8 microfarad capacitors have a potential of 36 volts. So this capacitor splits that difference, and so it has 18 volts. That's B. What is the equivalent capacitance of this circuit? Well, to find the equivalent capacitance of capacitors in parallel, you just add them up. And so this circuit simplifies to just a 6 microfarad capacitor. That's 1 plus 5, and a 12 microfarad capacitor. That's 8 plus 4. And then for capacitors in series, you have to take the inverse of the sum of the inverses, and that is that the equivalent capacitance is equal to 1 over 6 plus 1 over 12. See, that's 2/12 plus 1/12. That's 1 over 3/12, which is equal to 4. So 4 microfarads, which is option D. Alright, what is the charge on the 4 microfarad capacitor? You need to remember this rule, that capacitors in series have the same charge. Alright, so the charge on the 2 and the 4 microfarad capacitors are the same. Likewise, the charge on the equivalent capacitor that's made up of the 2 and 4 is the same as the charge on the 2 and 4. So first we need to find out what is the equivalent capacitance. The equivalent capacitance, just like I did before, is 1 over 2 plus 1 over 4. And that's equal to 1 over 3/4, which is 4/3 microfarads. And then I want to find out what is the charge on that equivalent capacitance. That's equal to the equivalent capacitance times the potential, which is 4/3 times 10. 40 over 3, let's see, which is equal to 13, roughly. Alright, so the answer is D. This figure shows a capacitor with plates of area equal 1 square meter and distance between the plates of 2 times 10 to the minus 4 meters. Insulator's dielectric constant is 10. Place between the plates was capacitance. This is simple calculation. C is equal to kappa epsilon naught A over D. Kappa is 10. Epsilon naught, permeativity constant, 8.85 times 10 to the minus 12. The area is 1 square meter. The distance between the plates is 0.0002 meters. And that gives us an answer 4 times 10 to the minus 7 farads. That's not given as an option, so it has to be one of these microfarads, either A or B. I always like to write out all the decimal places because it's kind of it's a little more difficult. Let's see, 0.000004 farads. That's 4 times 10 to the minus 7. And I know that a microfarad, that micro is going to move it over 6 places, so that's going to be 3, 6, so that is equal to 0.4 microfarads, which is B. Or you can do the normal unit conversion as we've done before, and that's fine too. Capacitor C1 is connected across a battery of 5 volts. An identical capacitor C2 is connected across a battery of 2 volts. Which capacitor has the most charge? Well, I know that Q is equal to CV. If C's are identical, which they are, because the two capacitors are identical, then the one with the higher voltage has the higher charge. And the one with the higher voltage is C1, that is B. Okay, 2 wires, A and B, are made of the same metal and have equal length, but the resistance of wire A is 4 times the resistance of wire B. How do their diameters compare? Well, we know that R is equal to rho L over A. The resistivity, which are the same for these because they're made of the same metal, L, which is the same for these because they're equal length, and then the area, the cross-sectional area. And those aren't the same, obviously. And so we want to know, how do their diameters compare? Well, first, we know that RA, the resistance of wire A, is 4 times the resistance of wire B. It means that the resistance of wire A is bigger than the resistance of wire B. If the resistance of wire A is bigger than the resistance of wire B, that means that the cross-sectional area of A is less than the cross-sectional area of B. Alright, so that gets rid of options A through C. So now we're just looking at D and E. And further, we know that the area of A has to equal 1/4 of the area of B, because then that would give us this relationship, this factor of 4. Because remember, the area is an inverse relationship with the resistance. Alright, so the area of A has to be 1/4 of that of B. But we're not asking about area, we're asking about diameter. And I know that area is proportional to the square of the diameter. And if I square the diameter, that means that I have to have a factor of 2 for the diameter. So my diameter of A is 1/2 the diameter of B, and that's option E. Okay, when you rotate the knob of a light dimmer switch, what is being changed? Alright, the current is being changed. That's what causes it to go brighter. The power likewise is being changed. The voltage on your light remains at 110, 120 volts. Alright, so that doesn't change. And the resistance is changing. Physically, that's what you're changing when you rotate the switch, is that you're changing the resistance, and that in turn changes the current, and that in turn changes the power. Alright, so the only thing is the voltage that is not being changed. So that's 1, 2, and 4. It's option A. 2 space heaters in your room operate at 120 volts. Heater 1 has twice the resistance of heater 2. Which heater carries the greater current? Alright, this is similar to a concept test question that we asked in class, but in that question it was dealing with power. This question is just dealing with Ohm's law. V is equal to I times R. They both operate at 120 volts. Heater 1 has twice the resistance, which carries the greater current. The one with the smaller resistance is going to carry the greater current, because if R is small, I is big. Alright, so the one with the smaller resistance is heater 2. So the answer is B. 20 volt potential difference is maintained across a 10 ohm resistor for a period of 30 seconds. What total charge passes through the wire in this time interval? Well, I is equal to V over R. It's 20 volts over 10 ohms, which is 2 amps. And then the charge is just the current times the time. That's 2 amps. The time is 30 seconds. An amp is a coulomb per second, so that gives us 60 coulombs. The answer is C. Entergy charges its customer about 14 cents per kilowatt hour. How much does it cost to run a 60 watt bulb for 12 hours? A number of different ways you could do this. Let's just figure out what are the kilowatt hours for this 60 watt bulb for 12 hours. Well, 60 watts is equal to 0.06 kilowatts. Moving the decimal place over 3 spaces, 0.06 kilowatts. So I get 0.06 kilowatts times 12 hours gives me 0.72 kilowatt hours. Alright, and then I'm charged 14 cents per kilowatt hour. So to find the amount of money is 0.72 times 0.14. Let me write out the units here. 0.72 kilowatt hours times 0.14, that's dollars, per kilowatt hour. So my units cancel there. I'm left with money, and it gives me 1 cent. Or excuse me, 10 cents. So the option is D. So to run a 60 watt bulb for 12 hours costs you about 10 cents. Current of 20 amps flows through a wire of length 1 meter. Cross-sectional area given. Potential across the wire is 1.4 volts. From this table of resistivities, select the material of the wire. Well, I know that resistance is rho times length over area. I want to calculate the resistivity. That is equal to rho A over, or excuse me, R times A over L. However, I don't know the resistance, but I know that V and I, the potential and the current, and V is equal to IR, so R is equal to V over I. V is 1.4 volts over 20 amps, so that's 0.07 ohms. So I can plug in these numbers. I have 0.07 ohms. The area is given, 7.85 times 10 to the minus 7. And my length is 1 meter. That gives me 5.5 times 10 to the minus 8 ohm meters. And just go through here, that is tungsten, has that same, so the answer is D, has that same resistivity. 3 volt potential is maintained across a 10 ohm resistor for 2 minutes. How many electrons pass through the material? It's very similar to what we've done before. First find the potential, or excuse me, the current. I is equal to V over R. That is 3 over 10, 0.3 amps. Q is equal to IT, that's 0.3 amps. That's in coulombs per second times 2 minutes, which is 2 times 60 is 120 seconds. So that gives me a 36 coulombs. That's the charge, but that's not what I'm asking. I'm asking for the number of electrons. So I want to convert this to number of electrons. So 1 electron has a charge of 1.6 times 10 to the minus 19 coulombs, and that's 2.25 times 10 to the 20 electrons. That is option C. A 50 ohm resistor is hooked up to a power supply of 150 volts. What amount of energy is dissipated across the 50 ohm resistor in 3 seconds? Well, power is equal to V squared over R. These things are already given, 150 volts squared over the resistance, which is 50 ohms. And that gives me 450 watts. But I want to know the energy in 3 seconds. Energy is power times time, because power is just energy per unit time. So that's 450 watts, which I'm going to write as joules per second. That's what a watt is. Times 3 seconds gives me 1350 joules. So the answer for that is A, and then 26 of course is B.